Thank you, David, for warm introduction. Actually, this is my second time at NorthSec, and I'm really pleased to give a presentation on this stage with other speakers. It's a really great event. And today I will be speaking about distributing reverse engineering for large-scale malware processing. In a nutshell, we have a large collection of malware, millions of samples, and we wanted to distribute reverse engineering of this collection across a small cluster. This presentation is co-authored by me and Alexander Matrosov. He is not here today. He is a security researcher with Intel in the United States. But however, I would like to give also credits to Gabriel Barbosa and Rodrigo Branco. Those are researchers with which we collaborated on this research, which was originally presented at Black Hat 2015. And at the bottom of this slide, there is a reference. I will start with a small disclaimer that opinions presented in this presentation does not necessarily reflect the opinions of our employers, and we are responsible for all the results or mistakes and whatever, so blame us, not our employers. And let's start with the picture of the hardware. So basically, this is a small cluster that we were using in this research. You can see everything is well set up. We had about 9 machines, and there is even like an AC here to cool down the system when it works really hard. But however, if you look at the different angle, there are still some room for improvement. And interestingly, that we were working on this research in July, June, and it was really hot in Oregon, Hillsboro. And their electricity at some point went down, so we're really thankful for fire detection and smoke system, which prevented from a disaster. So I hope Rodrigo's insurance company won't see this slide. And here is the agenda of today's presentation. So we'll start first with your introduction and explain our objectives and motivation. Why did we do it this way? And why did actually we started this research? And then we will go to a detailed overview of the process. How did we process malware, which are machine learning algorithms, which are malware analysis algorithms we were applying to them. And then we will go to the discussion of the results we obtained. And finally, we will present some validation of the methodology and tool set to be able to confirm that our approach that we are decided to take is correct, or it contains some flaws and needs some improvement. And then I will wrap up with the presentation with some conclusions and acknowledgements. So basically, they're one of the most, so about the motivation, I think their presentation of Olivier Bilodeau and Hugo yesterday about DevOps was a very nice explanation that the malware is growing within absurd space and we need to have a scalable analysis environment. So that's what we tried to build, because right now the process is focused per single sample analysis, and this is mostly manual work. So we decided to try to scale our analysis algorithms for large collection, and we also tried to provide research material for the researchers in this area to be able to contribute as well, to use our results and build their research on top of them. So the objectives were just to demonstrate the possibility of in-depth large-scale malware analysis, and I want to highlight here a word in-depth, because right now there is quite a bit of a frameworks that can that allow to do analysis, but in most of the cases it's quite shallow, and they're allowed to do some kind of filtering whether this is malware or not. But in-depth we mean a complete disassembly of the malware sample. We also tried to distribute across the cluster IDA-Pro with Hextrace decompiler. So why did we pick up IDA-Pro? Because this is an indispensable tool for malware analysis. It is widely used in the industry. And so we were kind of interested in, okay, so if we can do this automatically in a batch mode on the cluster. And another objective is to share with the community all the information that we generated, IDB files, or scripts, or dumped intermediate representation, and so on. Let's speak about the scope of this research, the scope of the project. So we limit the sample set to only 32 and 64-bit P executables. That means are executables for Microsoft Windows platform, which were not packed. We were using mostly static analysis. Why static analysis? I will explain on the next slides, but we were doing only static analysis. For this reason, we need to have unpacked samples. We didn't impose any restrictions on the size of the malware, so we had a processor in our collection samples as large as several, like tens of megabytes. And we were given a preference to Microsoft Visual C++ compiler. So we analyzed samples compiled with Microsoft C++ because of using our Hex-Race Code Explorer, which works right now only with their Microsoft Visual C++ object-oriented types. And we were using this cluster, which Rodrigo and Gabriel worked on, and they presented this result at Black Hat 2012. So this paper contains the complete description of their infrastructure. But in brief, we have about 9 machines. They're sharing 72 cores and 100 gigabytes of RAM. And here is the brief overview of the methodology and of the process. So we started by pre-processing. So we take our samples from open sources and started to filter out. So we filtered out everything what's not 32 or 64 bits or non-packed malware. And I think in the input we have about almost 8 million samples. After filtering out all their samples that don't meet these criteria, we started with running them in the analysis environment and applying different machine learning malware analysis algorithms, and we were obtaining results from their decompilation and disassembly, and we're storing them in the local file system in files. At the next step, we did structuring and aggregation of the information to be able to process this, to compute some statistics, or to do data analysis. That was done in phase number 4. This research, we were using our only static analysis for the following reasons. Generally, dynamic analysis takes longer time than static analysis, and since we had a very large sample set, for us, the performance was really crucial. So in static analysis, you don't have to spend like overhead time for setting up the execution environment. We're just loading the file or in the disassembler, and it works pretty fast. Unless there is their sample obfuscated, packed, or exploits a vulnerability in their analysis environment. Of course, there are some limitations. For instance, when you're disassembling, you need to make sure that there is a good coverage of your disassembled code. For instance, there is some dead code which your disassembler is not able to identify. It's not reachable from the entry point. But however, IDA has very nice heuristics, and generally it provides a very nice coverage for your disassembly. So that's why we decided to go with this tool. And in addition, we use the following additional software to get additional data. So we used our Hex-Race Code Explorer to dump C-trees of some IDA-recognized functions. I will explain what the C-tree is later, but so far you can consider C-tree as an abstract intermediate representation of your decompiled function. And we also were extracting object-oriented types from the file using Hex-Race Code Explorer. When dumping C-trees from their IDB file. So an IDB file is basically, I'm pretty sure everyone knows, this is your file where IDA stores all the results of the disassembly. So I will be frequently using this acronym IDB file to refer to the results of the disassembly. So we were computing C-tree depth, like how far this function is from the entry point in the call hierarchy. We were also interested in seeing how many malware is actually using the new instructions, which are hardware implementation of the advanced encryption standard, and your GetSec instruction, which works with the Intel technology SMX or safer mode extension. Additionally, we were doing study of this pointer usage. So this pointer is an implicit pointer, which is used in object-oriented languages to refer to the instance of the object. And we were paying attention to its actual implementation within the code. For instance, Microsoft or Visual C++ is implementing this pointer by means of an ECX register or RCX register, if we're speaking about 64-bit platform. But however, sometimes when you're doing some optimizations, it can use other registers, ECI or EDI register. So we're really interested in looking how actually pointer this is implemented here for these compilers. And we're also were analyzing cryptographic functions implementing cryptographic primitives using the IDScope plugin. So let's take a look at how this process works regarding dumping C-trees. So first, we loaded a file in their IDE Pro. We waited until their auto-analysis is completed, the functions are identified, and we started by enumerating those routines in their disassembled files. And we started with their dumping. So we processed a certain number of the routines because like some IDB files, they contained up to 1,000 routines and more. And in this case, we don't have much space to store first all the data. And secondly, not all the data are really interested because, for instance, there are many small routines which are just contaminate the data set because they present in every sample. So we decided to filter them out, and as a result, we were processing first 60 routines of size larger than 1/16 hexadecimal. We were processing 30 crypto routines identified using their advanced encryption standard or spotted by their IDScope plugin, and we were processing the first 60 other routines bigger than 60 bytes. Those constants, 60 and 1/60, were chosen empirically, using our experience and during the manual analysis. Once we find a function, we decompile function using hex-raised decompiler. As a result, we obtain intermediate representation C3, and we serialize C3 toward a string. But before serializing, we are doing C3 normalization. Normalization is important to make sure that similar functions, they have the same C3s. For instance, you can imagine two functions where they're exactly the same, except in one function, the local variable is initialized with variable 1, and the second function, the same local variable is initialized with value 2. So those functions are very similar, and we want to have exactly the similar C3s, but since the different initializers are used, C3s will be different. So during normalization, we're filtered out everything from the C3, which is not really relevant, to keep the general structure of the function and to dump it. So I will say a few words about this later. Next thing, we dumped information about object-oriented types. The object-oriented types contains two interesting properties. First, the virtual table, which contains pointers to their polymorphic methods, so basically methods which were overwritten in their subclass. To do this, we were finding all the references to these pointers within their IDB file, and we were looking for virtual tables which were stored in the following sections: our data, or a section with any other name but with the data attribute. So usually Microsoft Visual C++ compiler puts them in the our data or data, but sometimes due to obfuscation, the sections may be renamed, so we analyzed all the data sections, and we were finding all the cross-references to virtual tables within the IDB. Later, we used some heuristics to determine the size of the virtual table and the total number of the methods in this virtual table. The code, those heuristics, they are available in GitHub account for Hex-Raised Code Explorer, so you can go there and see how we're doing this. And once we recognize virtual table, we create structure representing this table and include this in the result. In addition to finding virtual tables, we also did reconstruction of their types attributes. In order to do this, first we identify an instance of the object within the IDB file, and then we find cross-references to its constructor. So And once we go into the constructor, this is the part from where we actually define the attributes, because let's say most of the attributes, they are initialized within the constructor. And once we go within the constructor, we can see, okay, this is this, it points to this buffer, and we're actually tracking all the references to different offsets within this buffer with the size of the reference. So basically, this defines the layout of the type. We are filtering types which contains only 3 attributes or more, because there are actually many types. When we first started to run this on a smaller sample set, we got many types which contains 0, 1, or 2 attributes, and this is not really interesting for the results. So we are filtered out small data types and left only the ones which have 3 attributes or more. One dump in C trees, we're computing how far it is from the entry point and the total number of the cross-references. For this, we enumerate cross-references to this routine, and we used a breadth-first search algorithm to find if we can reach an entry point from this routine. And we limited our search to 100 nodes, just to make sure we're not running infinitely. And once we find an entry point, we calculate the distance from the entry point and the total number of the cross-references. When it comes to identifying our advanced encryption standard, new instruction set, and GetSec, we used a linear sweep approach in this case, because it is faster. So we always start processing with the section where entry points point at. And we scan first half megabytes of the section. We use a linear sweep disassembler. And once we identify GetSec and advanced encryption standard instructions, we look for 15 instructions before and after to see if all these instructions are correctly disassembled. Because this may be the case if we're, let's say, start disassembling instruction not from the right offset, but let's say from the middle of the instruction, we get the AS instruction, and then there is some bad instructions, so that means that we're probably not doing this in the right way. Regarding this usage study, we were checking up to 5,000 calls within each IDB file, and we were analyzing 5 preceding instructions to a call to see if there is a loading of the ECX register. We use some heuristics to find if the ECX register is being loaded with some value. For instance, it is a move instruction or load effective address. And once we identify all their calls which are loading ECX register, we compute their percentage and they're included this in the results. A few words about distributing IDAPRO. We were really surprised with the performance we got using IDAPRO, because actually we were a little bit skeptical about this, because when you analyze your sample, or let's say your single sample analysis, IDAPRO is a kind of interactive disassembler. It shows you a lot of dialog or boxes trying to choose different parameters for analysis. It does the auto-analysis, and once your auto-analysis is completed, you need to enumerate through the routines within this IDB file and do this in an efficient way. But however, the performance was really nice, and so yeah, it met our expectations. However, there are some problems. First, related to developing IDAPRO plugins, SDK. SDK is complex and they're quite poorly documented. Are there any people in the audience who developed your IDAPRO plugin or Hexrace? Please raise your hands. Okay, not too many people. And also the thing is that their signatures of the functions can change from version to version. So that means sometimes you have problems with the compatibility between different versions, let's say either 6.8 or 6.9. As I mentioned, we had a really good performance on commodity hardware. We didn't have high-end systems, like about 8 cores per machine and 10 gigs of RAM. And another observation is that most of the plugins, they were written for Microsoft Windows platform. Like they were using Windows API, they were using Windows types, or before making them work on Linux, because our environment was running on Linux, we had to apply some efforts to port them. Another observation is that most of the plugins are not made to scale, like they are targeting a single sample analysis as well as an IDA Pro. So that was one of the observations which were made. And interestingly, when we run IDA Pro with the plugins on a large sample set, we identified many bugs in IDA, in our code, in other plugins. So it was a very nice test. So if you're interested in testing your plugin, please send us, and we'll try to see how it works. And now I want to say a few words about their Hex-Race Code Explorer. I and Alex, we are developers of the Hex-Race Code Explorer. The first version was released at Recon 2013, and the latest version works on IDA 6.9. But however, some guys approached me and they told that there were some bugs in the code. So please, if you find the bug, you can go to the GitHub page and report it there. I think this was the most efficient way of reporting the bug. So there are numerous features in the Hex-Race Code Explorer. So originally it was designed to facilitate object-oriented code analysis and position-independent code analysis. But in this research particularly, we were using only one feature, which is extracting object-oriented type information from the binary. And right now I'm going to give some low-level information, because the Hex-Race Code Explorer works with their Hex-Race decompiler, which is using the C3, the intermediate representation of the decompiled routine. And here is the explanation of what actually C3 is. C3 is an abstract syntax tree which represents their decompilation. For instance, on the left-hand side or part of the slide, you can see here an expression, variable 2, variable 3 equals variable 2 plus variable 7. And on the right-hand side, you can see how this is actually implemented in C3. So you can see here, so if there is a mouse here. No, okay. So there is, oops, sorry. All right, so there is an assignment operator which corresponds to, there we go. Yeah, so there is an assignment operator here which corresponds to this equal sign. And so the variable 3 is located on the left-hand side of this operator, and on the right-hand side we have an addition which takes two parameters, variable 3 and variable 7. So this is the way actually how C3 looks like in the decompiler, and how it works with. So each block within C3 is of type CITEM-T, and CITEM-T actually is a base class for two subclasses, one representing expressions and the other one representing statements. So statements, basically, they correspond directly to the statements in the C language. These are the blocks or E4, while expression is something what has a type. So you need to make sure that the type information is consistent in the C3. For instance, if you're calling a function and passing it in an integer, then you need to make sure that their C3 block representing integer actually has a type integer. And this is the only requirement, because their Hex-Race SDK allows you to do whatever you want with the C3, but you need to make sure that the type information is consistent. And also, Hex-Race offers a convenient way for traversing those structures if you need to enumerate their blocks or do some transformation with them. Okay, so let's take a look how this is used in this research. So we did a type reconstruction. We reconstructed object-oriented types, and for type reconstruction, there are two essential steps. First, we identify virtual table, and a virtual table is related to polymorphic types. Because if there is no polymorphism, there is no reason for a virtual table, because all the functions, they are called directly. And virtual tables contains pointer to the functions which are actually overwritten, and recovering virtual tables gives us very interesting results about the type hierarchy. And another idea which we use is a type attribute identification, reconstructing type attributes. So for instance, here we can see that there is a virtual table identified in the IDB file. So it is here, and we can see that there is a cross-references to this virtual table and this function. So if we go to this function, this is a constructor. So we get a constructor, we have this pointer, and we have attributes in this object. So the idea is to reconstruct those attributes. This is actually what we are doing, and we are obtaining this structure representing the type and its attributes and their virtual table as well. Regarding normalizing the trees, so here is the implementation of their filteracy item routine, which does filtering of their blocks within their C tree, which are not relevant. So we're skipping some cast operations, some helper functions, and some other minor blocks. And for instance, here is the complete C tree of a function. And everything what is marked here with black or blue is included in the C tree, and everything what is marked with red is filtered out. And here are some general thoughts about like pros and cons of using hex-race intermediate representation. The good thing is that you are working with your not platform-dependent code, because your hex-race decompiler works with your 32 or 64-bit ARM, and you don't have to care about actual opcodes, because you're working at higher abstraction level, basically at source code level analysis. But however, there are some disadvantages as well. First, that the hex race is designed for single function analysis. Even though there is an option, you can just run, okay, decompile the whole function, but what you will get is not going to be a really accurate decompilation, because the results of a subsequent decompilation may invalidate or change results of the previous decompilation. You can imagine like you have two functions, function 1 and function 2, and function 2 is called from the function 1. So you first decompile function 1, then you go to decompile function 2, and during the compilation of the function 2, hex-race identifies some parameters that were not identified at the decompilation function 1. And as a result, the signature of the function is changed, and you need to go back to function 1 and decompile it properly so that you can see a proper call to the function 2. So this is one of the limitations and constraints we are faced at this research. Now let's go to the results we are obtained by analysis of all their intermediate representations we obtained while running this on a cluster. So I included a subset of the results. The complete version is available in the Black Hat talk and the Black Hat presentation. So first, we started with preprocessing of 7.8 million samples, and as it appears, like only 31% of them were not packed. So this is the sample set we were using, and out of this 31%, 13% was only using our Microsoft Visual C++ as a compiler. I think that the most popular packer was UPX and its modifications. Here is the results of their use of this usage study. So on this slide, we can see a table with the top 10 percentages of this usage, like how many percentage of the calls that were loaded in E6 register. Well, actually, I don't see here any interesting like a function of loading E6 and their prevalence of the percentage. Like we have a maximum at 4% of calls, and however, we can see also a high value of 66%. So from this point of view, like we try to use this identification, this E6 registry XX register identification to be able to automatically filter out your code which is using objects like object-oriented model or not. So for this reason, we've chosen a threshold to limit which is around 1 or 2% to be able to filter out. If we have percentage less than this, we consider that this is not object-oriented code, and we're not going to consider this in the research. This is the information on the top 10 repeated C trees. So in total, we have 8 million C trees dumped and obtained from the samples. And some C trees are like very frequent. We had 40,000 C trees, which is 0.4%, and this most one is 14,000. And if we take a look at their unique C trees, we find that 30% of these C trees are shared between different samples, while 70% are pretty much unique or on their pretty much unique to specific samples. So this is an interesting result, which requires a further investigation because it's not sure. I was really surprised with this ratio because I was expecting to see larger portion of the C trees shared between the samples. Maybe the normalization is not well configured, and we need to filter out more results. So this is regarding the unique C trees. And however, if we take a look at this approach, but from the point of view of the samples with repeated and non-repeated C trees, we can see that 9% of the samples contain, so 9% of the samples, they are sharing between each other C trees, while 91% are not sharing. When it comes to C trees reaching entry point and their average and standard deviation of their depth, we can see that roughly 50 C trees that we dumped were able to reach the entry point, and the average depth is 5. So that means that most of the C trees we dumped is 5 calls away from the entry point. So these results might be interesting for, let's say, those who are developing emulators, because sometimes when you're emulating the code, you need to know where exactly you need to stop during the emulation. And like having an average depth of 5, that means that you need to emulate up to 5 call depth to be able to reach those routines which we were dumping. And here is their C trees with their cross references to them. We put here maximum 10, the top 10 C trees, and like we have one C tree with 11,000 cross references to it. So this is a pretty high, and this is an outstanding number. As we can see in this table, this number of parents is steadily decreasing. So yeah, and you can go to the original version of the presentation to get complete results. In the last part of the presentation, I'm going to speaking about the validating their methodology we were using, because we run these algorithms on a large set of malware, and then we wanted to apply the same algorithms to a smaller set, which we know is related, to be able to validate and see how well it works in this case. So here is the timeline of the modern C++ malware used in targeted attacks. There are different groups identified: Stuxnet, DoCore, Equation, and Animal Farm. So for this case, we choose your Animal Farm case study because we know that this malware is written in C++, and they're all related. And there is a very nice presentation on this topic presented at Aricon last year, Totally Spies, where you can get all the complete information on their analysis of this malware family. But a briefer introduction to it: it was discovered by Canadian agency CSEC as an operations law globe, and it was written in our Microsoft Visual C++. So that's actually what we wanted. So we applied our algorithms to these malwares, and we tried to compare and find some similarities. For instance, here you can see the comparison of Kasper's and Dino's virtual tables found in the output of our tools, and we can see that there is some intersection. there are two objects, the run key and autodel, which are shared between those two samples. So that means our virtual table approach or identification works here. And there is a definition of the run key. So the run key defines how malware communicates with the registry. This is a base class, and there are some subclasses which define particular implementations, like the malware can access register directly by API using command prompt, using Windows management instrumentation classes, and they're from reg command. And autodel defines how malware actually removes itself from their system after infection. And there are also different subclasses related to API using move file to remove itself, or using command prompt, or using Windows management instrumentation classes. And usage of this, each particular subclass depends on their parameters on the configuration parameters of the malware. So we did identify the similarities, and we tried to reconstruct their object attributes. So here is their, on the left-hand side, you can see the Casper's run key constructor, and on the right-hand side, you can see Dino's run key constructor, and there is a significant difference here. Because in case of the Casper, each object is created depending on their configuration value. So, for instance, if there is a AV strategy run key API is set, it creates only an object with run key API. Otherwise, if there is AV strategy run key registry, it creates only an object with run key registry. While in Dino's case, it creates one large object which contains other objects as sub-objects. And if you try to reconstruct the virtual tables, we will see that they're not equal, and in this case, our approach doesn't work. Okay, let's go further, and we compared also Dino's virtual function tables with nbots. Again, we can see that there is an overlap in virtual tables. So here again, our virtual table algorithm works well. We are able to identify the intersection of the same virtual tables, so that means they share similar code. And if we go to the constructors, they are pretty much similar. Not 100%, but they are very similar. And if we try to identify or reconstruct their attributes of the structure, we will get the same, exactly the same structure. So here it works well, and it's very nice. So here's the table which summarizes their shared types between different malware families. We can see that most of them share a lot of code between each other. And it's also interesting to see that there is some small difference between Casper and Dino. The Casper contains implementations of run key VMI and autodel VMI. And Casper appeared after Dino. That means it was an evolution of the Dino. So they reused code in Dino by adding additional functionality. And here is the same information, but from the different point of view, the number of their shared types are in these malware families. Yeah, we can see that the Dino and Casper are highly correlated, so they share a lot of reused code. So to conclude the presentation, what we did, we actually distributed IDA-Pro. So we demonstrated that our IDA-Pro can be distributed, can be run in large scale in batch mode, and but however there are some actions that we need to apply to make them run, and there is a call for plugin developers. It would be a nice option if you also add a special batch mode for your plugins, not only for interactive work with the user. And of course, if you want to test your plugin on millions of samples, you can send it to us, and we'll see how it works. And we also will be releasing a special version of your Code Explorer for NorthSec conference. We're going to release it Control-Z, yes, sir. Actually, yeah, a few things like we were actually going to release it before, but we need to do some code cleanup. So as Olivia told, it couldn't take quite long, but we hope it will be done soon. And again, it's 21st century, and there is no Control-Z in Hextrace Code Explorer. So this is actually where we are going to address in NorthSec edition of the plugin. So this will be one of the biggest improvements, and we also will add a major feature extract and type information in C-trees in JSON format, because right now it's dumped into their custom text file, which is not really good, so we'll fix this one. And here are some thoughts for future work, which we're going to do, what we would like to concentrate on. Maybe you have different feature requests, so please let us know. One of them is pattern matching for C-trees. Let's say you can find in the IDBR functions or by C-tree pattern. You say you input this C-tree pattern and it outputs all the functions which meet this pattern. This might be useful for the vulnerability research, crypto identification, integration with OpenRail. So not only use the IDA and Hextrace Code Explorer as a base tool, but also use the OpenRail project released by Crush. And if you have any bugs and features, so please submit them. If you're interested in the project, you can discuss Code Explorer on Orihin's Gitter channel. So we're really looking for the feedback. And before I conclude the presentation, I would like to say some acknowledgements to our employers and to our Ilfai Gulfanov and Hextrace team for their support of this research. Without them, this research wouldn't have been done. So thank you. And that's it. Thank you for your attention. If you have any questions.